this is my recollection, just going through the notes, what we've discussed. We started last week. First lecture was on revision, what you've done in your first year. So we went through static equilibrium conditions, so summation of forces, summation of moment is going to be 0, the different types of support and the reaction forces you get at them, the different types of loads you get in the beam, and the sign convention that we're going to adopt, and then the different types of structural elements, tie, strut, column, shell, so things like that. And then we discuss how to find bending moment at any location along the length of a beam. Okay, so I think that's what I think you've done in the first year, but we need them here also. And then we've just finished the second part, which is on how to find bending stress. So mainly bending stress and bending strain. So neutral plane and neutral axis, and how to determine the location of a centroid for symmetric and non-symmetric. The assumptions that we use to derive the equation for the bending stress. So, and the relationship between the location of a centroid and neutral axis for symmetric and non-symmetric when it is subjected to pure bending, and also bending and axial load. And so how to find second moment of area for along any direction. So one first along neutral axis, and also about a line that is parallel to the neutral axis. Then we went through, in the derivation of the bending stress equation, the main concept of equilibrium, that the stresses that are developed in any structure must be in equilibrium with the load that you apply to the beam. And we'll be using that again, I think, in about two weeks' time, towards the end of this course. We then went through the bending stress equation. So to find the bending stress anywhere along the length of the beam and anywhere within the given cross section of the beam. And then if you know the bending stress, you can use that to determine what is the maximum load you can apply to the beam to avoid the stress going beyond a given value. So that's all we've done. So that's how we do design for strength. In this case, the load is subjecting the beam into bending. We want to make sure that the stresses are not too high, that the beam will break. So I brought this very flexible beam here. So if that bends, the more we bend this, the more that side get into tension. If you bend too far, it will just break. It will break right there. So what we're trying to find is what is this maximum stress, or the load you can put on, to make sure that you don't break this. So if you do that to this, I'm sure you've done that at home. The more you bend, if you bend too far, it will just break. It will just break there. Right, so that's what we've done. So we focus on stresses. Now we're going to go to the next section. Now we want to focus on the magnitude of the deflection. So I've used this. So if I do that, so that is deflected. We want to find what is the magnitude of deflection if you go from the initial plane as you go downwards like that. So what is the magnitude of the movement? Okay, so let's look at that. So that's the next thing. So this will take us both today and tomorrow. We'll do the basic derivation today, and then we'll do the solution to the three questions that I have at the end there. I've listed there what will be, I think, at the end that you will be able to know. So why is it important to determine the magnitude of the deflection and the relationship between the load and the magnitude of the movement that you get there. You got a question? No? Okay. So let's start with that. So why do we need to bother about why we need to deform? It's a shame. All the beams here are now behind the ceiling, so we can see them. So, but here you will have a beam across like that. So, and that beam, one of them is actually supported by this long pillar. There'll be another one behind there. There's a load on it. So we cannot see that it's not moving, because that's been designed to make sure that it doesn't deform to a level that you can see. That's the first one. So you don't want any movement that will make the structure look strange. So that's the first one. The second one is you also want to set a limit to the maximum value of deflection that you are allowed to have. In the design of buildings, the British standard actually specify that the maximum deflection you should have in your beam should not be greater than 1/360 of the length of the beam. So once you have the length of the beam and you calculate your the maximum deflection, you have to make sure that it is less than 1/160. If it is not, then you have to go back and change what you've got there. And there are different ways you can reduce the magnitude of the deflection, which we'll be discussing. So you can change it without changing the load. Okay, so it's possible to do that without changing the load. So we want to go through how we find the magnitude of the deflection for a given beam and for a given load there. So there are different ways of doing that. I've listed them here. So the main one that we'll be focusing on this course is the one in bold. So that is the one we'll be doing. And the remaining three you'll be doing in your third and fourth year. In fact, the second one, that is the elastic energy method, you'll be doing, if you are doing my course again next year, then you'll be doing that again. So we only focus on that. So from the name, you can see if you don't know how to do integration, then you might as well go with this one, because you've got to be able to do that. So okay, so let's start. So our aim is to find the deflection in the beam that is subjected to some loading, and the loading has subjected the beam into bending. So we want to relate the magnitude of the bending moment to the magnitude of the deflection. Okay, so we've got a beam. So there's so I've got a beam that was initially straight. So there, and we've applied a bending moment. The bending moment is coming from the load. Okay, it's coming from the load. So the convention which we've adopted so far is that our x-axis along the neutral axis, we're always starting from the left-hand side, going towards the right, and y is pointing from the left, going downwards. So that's our general convention. And you will see the third one is the amount of rotation that we get. The convention is to go in the positive direction as shown there. So what we want to do is to find the magnitude of the downward movement of the beam relative to in terms of the magnitude of the bending moment that you've put onto it. So I will go through this. So I've got a beam which was initially straight, beam AB. Now it has deformed. We now have this curved beam. That is the deformed state, which is here. So I'm looking at point C and point D. So I want to look at what is the downward movement of point C, what is the downward movement of point D, and I want to use that to relate that to the magnitude of the bending moment that we have in the beam. And so with that, we'll be able to do the rest. So point C is at the distance x. So initially, and it has moved down by a distance v. V is the actual displacement that we are trying to find, and we want to find that in terms of the magnitude of the bending moment. Point D, which is at a distance x plus dx, has moved down by another smaller amount, v plus dv, as shown in that particular diagram. And the arc between them, that arc there has got a length of ds. So the diagram is self-explanatory. So if you look at the one in red, you might want to change that there. So that should be theta minus d theta, not theta plus d theta in your notes. So if I look at point C and I draw a tangent to where point C is, I can look. So that gave me the magnitude of the rotation. So that is the angle theta. If I draw a tangent at point D, that angle has decreased a small amount by d theta. So that is all I need to relate the movement downwards to the actual magnitude of the bending moment. So when I go to the next page, I'm going to redraw that again, and I will be able to show what we want to show.
So can you go back to that previous one quickly?
Which one? This one?
Just take the picture.
Right. So if we look at the form shape, what we have is point C with a small arc of length ds with an included angle of d theta. Radius of curvature is r. So if I redraw that, so right on here, I'm going to do that at the top. So what we have is where that is r, that is r, that is d theta, and that is ds. So if you look at that from your geometry, so it is clear that ds will be r d theta. So from geometry, so and which then implies from that 1 over r equals d theta ds. But if you look at the diagram which I showed on the previously, is that as we move, let me just take this away and use that to explain. So as we move from C to D, that angle there continues to decrease. So as we move along that curve, so as you increase S, your theta is going down. So if you increase S, you decrease theta. What that means is that d theta ds is actually negative. Because as you are increasing one, the other one is going down. But because the radius of curvature is always a positive number, so you cannot have a negative radius, so it's always a positive number. In order to make sure that this expression here remain a positive number, we must have a negative sign there, and that's why we've got that. So that's the first one. Now let's look at what the next stage, where we now want to relate it to the applied bending moment.
Did you say that if you increase the angle, the distance decreases?
No, it's not. If I go back, the angle theta is the actual tangent. So that's the point.
Mm-hmm.
So I draw a line that is tangential to the curve at point C, and the angle that it makes with your initial direction is theta. Okay. Okay. So and as you go this way, that angle continues to decrease. Okay. So if I redraw that, I'm going to make it slightly bigger. So if I redraw that again, so right here, so I'm going to draw the initial direction like that. I'm going to draw that curve. Hopefully I'll get this right. So let me say we got like that. So that's the form shape. So my point C, I'm assuming my point C is there. My point D is somewhere here. So we have a curve, which is like that. So the vertical movement of point C is V. That's our point C. And the downward movement here is V plus dV. That is V. That is dV. So point C has moved down by vertical distance V, which is what we are trying to find. Point D, which is slightly further down, has moved down by V plus dV.
So can you draw in the theta as well, please?
Sorry?
Can you draw in the theta?
Yeah, don't worry, just calm down. I will get there. Okay, so that's the actual downward movement. Now I want to do the angle theta. The angle theta, hopefully it will work, is the tangent that comes from here. Is the tangent to point C. So, and that angle there is theta. Okay. So if we go back to the definition of radius of curvature, so the radius of curvature, see if I can find different color. So the radius of curvature will come from here, like that, and from here, all the way like that. So if you have a circle of radius r, if you draw a tangent to a circle, the tangent is at an angle 90 to your radius. So this angle, the tangent here makes an angle of 90 degrees with that. Yep, I hope from your school geometry. Yep, do you remember
It's
that?
not the same angle that would appear on the top, right?
Which one? Which angle?
Well, it's not determined here. The one,
Which one? This one?
yeah.
Yeah, that one is just a small change in angle. You're going from there to there. That would be d theta.
So it wouldn't equal to the one on the left. That would be completely different.
No, it would be different.
Yeah.
Okay. So the one on the left is the tangent to a point C, making with your initial horizontal direction. But your point D has moved slightly further down. Your point D is moved by a small angle d theta. So that angle is 90 degrees. So I'm going to go around and work out what all those angles will be. So if this angle is theta, if you just follow me, if that angle is theta, this is 90. This angle here is 90 minus theta. Yeah, can we see that? Because that is a triangle, that. That is 90 minus theta. This angle here is theta. And this angle here is 90 minus theta. And the angle here is theta. So what I'm going to do now, if you can see that, so theta, 90 minus theta. So I'm going to draw that small triangle below here so that we can see a bit clearly. So what I now have is something that looks like this. dv dx theta. So that is a triangle from C to D vertically up like that. So that is this triangle here. Going from here, horizontally, vertically, and then going back up like that. So that is the triangle there. That is all I need to find what we are trying to find. So what is this one here? That is our C, that is our D. What is that? What is the diagonal of that triangle?
Square root of dv squared plus dx squared.
Yep. That's nice, but that is very, very complex. Look at what we have at the top. See if you can see that at the top. We got ds there. So this one here will be ds. Okay, so let's work with that. So that is the only thing that we have to do. So the rest should be straightforward. So we have ds there. Remember now, if we assume that our point D is only a very small distance from point C, that is, it is not too far away from point C, then we can say that ds, that is not too different from dx. dx is the horizontal distance from C to D. If we have that. Sorry?
Why do we assume that?
Because we are always dealing with small deformation, and we are taking 2 points that are very close to each other. So that's why. So if we look at that small triangle, so what is tan theta?
dx over dv over dx. dv over dx. dx over ds.
ds over ds.
dx over ds. dv over dx. Oh no. dv over dx.
dv over dx. Thank you. Right. So that's right. That's correct. So we have dv over dx. Remember, we're trying to find v. V is the magnitude of the downward movement. So at the point, we want to relate that to the magnitude of the load, which is coming from our bending moment. So we have tan theta equals dv over dx. But if we are dealing with very small deformation, like we said, very, very small deformation, that angle theta will be very small because the deformation is not very large. So what is tan of a very small angle? If theta is very small, so what is tan theta? Theta. Yep. If theta is very small, then tan theta will be the same as theta. So we can say that tan theta equals theta equals dv dx. Okay. But we've just said that because point C and point D are very close to each other, our dx is very close to, is the same as ds. So we'll say this will be dv over ds. Yep. Can we see that? Yes, no? Okay, so that is all I need. So if I go back to 3.1, you see 3.1, we said 1 over the radius is minus d theta ds. It's minus d theta ds. So what is d theta ds here? If you look at that, theta equals dv ds. Therefore, d theta ds equals d2v all over ds squared, which equals d2v all over dx squared.
Could you explain this again, please?
Sorry?
Could you explain this question?
Yeah, so I think we've showed here that 1 over the radius of curvature is minus d theta ds, okay? And we found what theta is. We said theta equals dv dx. So if you differentiate d theta ds, that would be d2v over ds squared, or d2v over dx squared. Yeah. And that gives us 3, that gives us 3.2. And that is the only derivation that I need. So because if you recall what we did last week when we were talking about bending moment, we showed that 1 over the radius of curvature is also equal to the bending moment divided by the modulus and the second moment of area. So we now have 3.2 and that. I can equate them together. That gives me the relationship between the downward movement, which is V, and the applied bending moment. And that is the moment and deflection equation. And that is all I need. So V is what we are trying to find. X is where we are trying to find V. Okay, X is measured from one point on the left going towards the right. So we decide at what point that we want to find what V is. And M is the bending moment at the location that we are trying to find that vertical deflection. And E is the Young's modulus, and I is the second moment of area of the cross section that you've got. So what do I need to do if I want to find V from that equation?
Double integrate?
Double integration. So that's what I'm going to show next. I'm going to show I will do the double integration, and then that's it, and we can start to use it. So the only thing you have to remember, or maybe you don't have to remember, is this equation is already in that sheet of the formula handout, is if you are trying to find the magnitude of the beam deflection, you always start from this. So that's the first thing that you will write down, and then you then go from there. So let's see how we do that. So we're going to do the double integration. We do the first one. So what I will now have is I will try to integrate that, and I will have the integral of minus m all over ei dx, right? Plus what? So when you integrate, what do you have? So I will have an unknown constant, which I'm going to call C1. Okay, so remember our bending moment will depend on where you are along the length of the beam, as you will see when we start to use it. So now I want to do the second one. If I do the second integration, so I will integrate this again. I will have the integral of minus m all over ei dx plus C1x plus C2, because we are doing it the second time. So now we now have two unknown constants, which I will have to find. If I can find those value of the constant, then I can find the deflection at any distance x from the left-hand side. I can find the slope of the curve at any distance x from the left. Remember, that x is our coordinate that tells us where we are from the support. So, sure, you've all done EG 3007 last semester. Yeah? Did you? Yeah, I'm sure. Yeah, you did. So you were able to solve second order differential equation. Yeah, that's so disable. So what do we need to find the value of that, of constant C1 and constant C2? So in order to find constant C1 and C2, I will need to put in what is called the boundary condition. Okay, so I need to what is called the boundary conditions. That tells me is that I will look at the beam and I'll ask myself, what do I know about V along the beam? Is there anywhere along the beam where I know the value of V or the value of the slope? And you will see that as we go on. So the maximum deflection just like the one for the maximum bending moment is when I'm here. Is when the V dx equals 0, but not at the support. So if you want to find where we have how far from the support that you have the maximum value of V, we can differentiate V with respect to x, and we'll find what value of x will give us that value, provided it's not at the support. So that. Okay, let's see how we use that. So I've got one more page, and then I'm going to go.
What's the I?
I is the second moment of the area. Okay, I thought that is quite standard now. Okay, so just before we do the final example, so I will just go through the last page here. So we've discussed, I think, last week and also yesterday, how we design for strength. We are trying to find stress. We want to make sure that the stress does not exceed a particular value. This is here designing for what is called stiffness. Here we want to design for stiffness. So when you say that, it means that you want to control the magnitude of the deflection that you've got. So here, because it's bending moment, so it is dv dx, which is the rotation that we will have. So because of the bending moment, and that will be a function of where you are along the length of the beam. So what x is, it will be a function of the magnitude of the bending moment that you apply. So if you apply a very large bending moment, then it will deform more. It will depend on the magnitude of the modulus of the material. It will depend on also on second moment of area of the particular cross section that you are using. So for a given value of the bending moment, which depends on the load, and at a given location, if you want to minimize the magnitude of the deflection, then we will need to know what is called the bending stiffness. How stiff is the structure to the applied bending moment? And that will be magnitude of the bending moment divided by the maximum rotation that you get. If your bending stiffness is very high, then it means that the beam is more resistant to the applied bending load that you got to it. So it will not deform much. If your bending stiffness is very low, then it will deform quite a lot. So this for example will have a very low bending stiffness because it's very easy to basically bend it like that. So yeah. The bending stiffness, however, is inversely proportional to 1 over E. So if if I want to, if I want to get a low deflection, then I need to have something here that is very high. That's right. Okay, so let's start with the first one. So you will see how we use this. Let me just summarize what we have here. We've just said that the deflection, friction V, is related to the applied bending moment minus M over EI. So that is what I will start with, and then I will do my integration and then put my boundary condition, and then we can use it. So let's do the first one. So I'm going to start with the one that we've done many times now, which is this one. So, and I put there, we want to find the maximum deflection.
Can you go back to the first slide, please?
Sorry?
The previous slide, please.
Which,
This one.
right, so we want to do this. So that is a simply supported beam, which has got a uniformly distributed load Q. We want to find the magnitude of the deflection at any location along the length of the beam, and also the location and magnitude of the maximum as well. So we've already done this several times, so we can find the magnitude of the reaction support, the reaction at the support. We can find the magnitude of the bending moment anywhere along the length of the beam, and then from that we can go on. So let's start. So I'm going to start because we want to find the magnitude of the deflection. I'm going to write and say the 2V all over the x squared equals minus M all over EI. E is the Young's modulus, and I is our second moment of area, and I will come from whatever cross section the beam has got. So it can be that, it can be a box, it can be an L cross section, it can be an I beam, it can be anything. So you'll find I based on whatever cross section that you've got, and that is I about the neutral axis. So we're going to start from that. So I know I cannot use this unless I know what the bending moment is. So that's where we're going to start from. So we'll first find the support reactions, and then find bending moment M along the length, which we've done now a few times, so I'm not going to go through how to do that. So I will start with the first one, so it's very clear. To find the support, we draw the free body diagram. We put reaction support. Let's call that end A, and that is B. The net effect is to have a load at the center, which is Q multiplied by L. And if you apply the concept of equilibrium, which we've done a few times now, we can show that RA equals RB equals QL over 2. So we've done that a few times now. Now to find the bending moment, then I will start from the left. We always start from the left going to the right. So I will start from the left. So I would just make an arbitrary distance x. I want to find RA at an arbitrary distance x. I want to find that bending moment M. So what will be M? So what's the equation for equilibrium of moment about the cross section at x? So the moment there will be M from equilibrium plus Q x squared over 2 minus RAX equals 0. Is there anybody who cannot see that, who does not understand that?
What's the
What is what? Q?
QL, yeah.
What is QL? Right.
Just the
So is there anybody here who also doesn't know that, who's going to explain that? So QL, here we have a beam with uniformly distributed load over the whole length. So in order to find the reaction at the support, you need to convert that to what is called an equivalent downward force. And that is Q multiplied by the length, because this is uniformly on the surface. Okay? Right, so is this clear to everybody here? Yeah? No?
Just give us 1 second, please. Slow down, please. So you did a cut from the right?
Sorry?
You did the cut from the right.
Yes, you always start from the left-hand side, and you take any distance x. Okay, so, and then you make a cut, and you find what is the moment at that particular distance. Okay? So in order for this to be in equilibrium, you always have a moment acting at that cross-section.
So what does this arrow on the right stands for?
Which arrow?
The, next to the moment.
Which one? This one?
No, to the right,
This one?
to the left,
This one?
The
to
one
the
that
left.
is called, M.
So you have n bending moment, and there is an arrow downwards, the one to the left.
This one?
Yeah,
Yeah, that's the shear force.
but why is it here if we're doing?
So yeah, that's the shear force. You need to put it there. If not, this will not be in equilibrium. So if you have a force acting upwards, and you have that acting downwards, when you cut that, you always have a shear force acting on that surface. The shear force can be up or down. So I'll put it down, because that is my sign convention, that the shear force on that surface is positive acting downward. Our shear force is denoted by V, but we don't need to find the value of V here, because we are not interested in the shear force. But when you draw your free body diagram, you must always put your shear force there, because that surface will always have a shear force.
Why is M pointing upwards?
Sorry?
Why is M pointing upwards and not downwards?
M doesn't point upward. M is acting in anti-clockwise direction,
Yeah, why is it bouncing upwards?
because that's our positive sign for bending. So positive sign for bending is the one that bends the beam upwards like this. We did that at the start, so this is positive bending, and negative bending is that. Yeah? Okay.
Sorry, y x is squared?
Sorry?
X, y, the x is squared?
Where's x squared? All right, okay. I thought you did this in your first year. Right, so let me go through this again. And we did this last week as well. Right, so it's very similar to this. Okay, so it's very similar to this. So you have a very small section. You have uniformly distributed load of Q acting over a length of X. So the net effect of this is a downward force acting like that at the center, which is Q times X, which is half of X from here, half of X from here. So the moment of this, about this cross-section, is Qs times whatever distance this is, which is X over 2. You are taking a moment about that cross-section. Does that answer your question or not? Kind of. Okay. Right. Okay, I think I've got to move on here. So you have Qs is the net downward force. It's acting at the center. So it is X over 2 from here. Moment is force times the distance from the force to where you are taking the moment. And the distance from this force to here is X over 2. I have Qx multiplied by X over 2. Yeah, okay. Right, good. Right, let's move on quickly. So I want to write down what the moment is now. My bending moment now, remember our RA is QL over 2. So I can now say that my bending moment is QL over 2 times X minus QX squared over 2. So I have replaced RA by QL over 2, which we found at the top before. So now I can now apply our equation for deflection. So Okay, so let that down. So that equation there, if you look at the beam, because there is no any other load applied, that is the only load that we apply, that equation is valid from the left to the right hand side. I'll put x from 0 to L. But so that equation is valid from the left hand side to the right hand side. But if you have any other load applied before you get to the right hand side, then you need to take another equation for the second part, which you will see much later on. So now let's look at the magnitude of the deflection. So I'm going to write down the bending deflection equation again, and then we have to do the double integration, which we mentioned a few minutes ago. So what we now have is that d2v all over dx squared equals minus m all over ei. Now we know what that bending moment is. I'm just going to substitute that. We now have minus 1 over ei into ql over 2x minus q over 2x squared. Now I can now integrate that first. So if I integrate that the first time, I will have dv dx equals the integral of d2v dx squared dx. If we integrate that the first time, what will we get? So I will have minus 1 over ei equals what? What's the integral of the first term? QL over 4x squared. Great. Thank you. Thank you. I've got QL x squared over 4. Right? So that's the first one. And what's the second one?
Q over 6
QX
plus
3 over 6. Thank you. Of that plus my constant, C1. And then I'll do it again, because I don't know what C1 is yet, so we'll find out shortly. So I will do it again. I will do the second one. I want to find V equals the integral of dV dx equals minus 1 over ei. And then I want to integrate what is in that bracket. What would that be? That would be QL x cubed over 12 minus q x4 over 24 plus c1x plus c2. Yeah. So now I need to know what c1 is and what c2 is. In order to do that, I want to use my boundary condition. Boundary conditions are what do you know in terms of the deflection and what do you know in terms of the slope, dv dx in the beam. What's wrong?
I'm just trying to write all this and it's quite hard.
Sorry?
Can we slow down a little bit, please?
Sorry?
Can we slow down, please?
Slow down to do integration?
To write down everything and think at the same time.
Okay. Right. Okay. So now let's look at the beam. At the beam and look at what we know and what we don't know. So if you recall what the beam is, I'm going to bring out the beam again.
Can you show the whole page, please, the whole paper?
No, I only need to show the beam. Okay. So let's look at the beam. Let's look at the beam. This is my x. That is A. That is B. What will be the deflection at A, and what will be the deflection at B?
Minimum and maximum.
Minimum and maximum.
0.
Did I hear somebody say 0? Who said 0?
Me.
Good man. I owe you a pint. When the beam deflects, the role of the support is to hold the beam, to make sure that nothing goes past that support. So the value of V will be 0 at point A, it will be 0 at point B. So an X equals 0 at point A, and X equals L at point B. And those are our two boundary conditions that we need. In order to find constant C1 and C2, I need to put what I know about how the beam will behave. So I put here, what are my boundary conditions? I will say V equals 0 at X equals 0. That is the first one. Number 2, I'll say V equals 0 at X equals L. And we use those two in what we have here to find what C1 is and what C2 is. So there are two unknowns, two constants, therefore we need two separate conditions, and those are the two that we need. So if I put in the first one, V equals 0 at X equals 0, what will we get? So let's do the first one. So that's our V. So V at X equals 0 equals, that would be 0, that would be 0, that would be 0, and we have C2. So I have 0 plus 0 plus 0 plus C2. What that means, therefore, is that our C2 equals 0. I'll go back again. Now that I know what C2 is, we go back again and apply the second one. Put what is V when X equals L, knowing that C2 is 0, we can now find what C1 is. And once we have that, we now have the equation of V at turning distance X from the support as a function of the load that we've applied, which is Q. So let's quickly do that. So if I go to this second boundary condition, and I'll say V at X equals L, that will be 0, but it is minus Q over EI of L4 all over 12 minus L4 all over 24 plus C1L. Remember, there's no more C2 because C2 has been shown to be 0. So now I can find C1 from that. So if I move all of this to the left-hand side, I have C1L equals Q over EI, L4 over 12 minus L4 over 24. There's a factor of 1 over 12 in what we have in that bracket. I can take 1 over 12 out. I will have QL over 12. I will
What's
have,
happened to C2 then?
sorry?
What's happened with C2?
Is 0
Is 0?
from the previous part.
Thank you. Okay.
If it was equal something, you'd have to input that, right?
Yeah. So, yeah, but for this particular case, C2 is 0. Okay. So if we were to do that, so we will end up with L cube over 2 minus L cube over, L cube over 1, L cube over 1, and L cube over 2, because we brought a factor of 12 out, EI. And you can simplify that. So if you do that, so we can get C1 equals QL cube all over 24 EI. So C2 is 0. We now know what C1 is. I can now write my expression for V, and for the slope dV dx. If you can do that, I'll now say I'm not going to do the rest. Just a substitute C1 and C2. So once we have that, So both of them will depend on the load, which is Q, will depend on distance x. That is the point where you want to find the magnitude of the deflection. And so with that, we can now find the value of the deflection at any distance x from that support that you are looking at. If you want to find the deflection at the center, your x in this case will be the length divided by 2, and you put that in, the value of the load, the value of the Young's modulus, the value of the second moment of area, then you'll be able to find that. But B, you have to be consistent with your units.
How did you get 24 in the denominator?
This is L cube over 1, L cube over 2.
You gotta move it down.
Oh, right. Okay. So that's L cube over 1, that is L cube over 2, that is L cube over 2. 1 minus half is half. Okay. Right. So you've got to be consistent with your units, and I think that is key here. So if your I is in meter for example, your length has to be in meters. Okay. So your Q, which is the one we're looking at, has to be in Newton per meter or kilonewton per meter. And the Young's modulus has to be in Newton per meter squared. Don't mix meters and millimeters. Okay, so if you want to use length in millimeters, you have to make sure that everything is the same. If that is in millimeter to the power 4, that has to be in millimeters. That has to be Newton per millimeter. That needs to be Newton per millimeter squared. Okay, so I'm going to do 2 more tomorrow. Guys, is it tomorrow?
Thursday.
Oh, I'm enjoying this. I want to do it tomorrow, please.